talking about distributions and probabilities and things like that, and why all this stuff is important. Because if we know the characteristics, if we know the mathematical characteristics of a given distribution, what we can do is we can start to identify the probability of obtaining scores of a certain characteristic, assuming that we have some known distributional characteristics. And this starts to become really, really important, again, being the foundation for all of our inferential statistics. All of this is predicated on us knowing the distribution of a t-statistic. And if we observe a t-statistic of a certain characteristic, we can say this is likely, this is unlikely, and sort of starting to draw some conclusions from that, although that ends up being fairly complicated, but we'll get into why that is. Okay. But to this point, you know, we're calculating our descriptive statistics, means, things along those lines, standard deviations, as estimates of our corresponding population parameters. Remember, the population parameter is always what we're interested in. We can't get at the population, so drawing statistics, we're pulling statistics in, calculating those, but we understand that these point estimates are always just an approximation, right? If I take a sample of the average height of University of Wyoming students, even if I've got a big sample, I randomly selected 100 people, true random sample, I know that the mean that I get is probably not exactly equal to the population mean. And so what would be nice, our point estimate is our best guess. If I say the average, if I get something that says the average height of University of Wyoming students is 5'7", and you ask me, what's the population estimate, what's my estimate, or what's the population parameter, what's my, statistically my best guess, 5'7", because that's what I've got, it's my best guess. But I know that there's always going to be a precision there, right? I know that there's going to be some wiggle room, so some estimate of the extent to which some measure of the precision of my estimate, am I likely to be very close, or am I sort of maybe sort of quite a bit of ways off? Very, very, very useful. This is something we're going to put a huge emphasis on this semester and next, looking at the precision of our estimate. So I have an estimate of some population parameter. Is it any good, right? Solution here is going to be our interval estimates. Our interval estimates, these are our confidence intervals. These are giving us an index of precision of our estimates and also a range of plausible values for this population parameter based on the data that we have and given the assumptions of our underlying statistical model. Both of these things are very, very, very important, right? If I say I want to get an estimate of the average height of all human beings existing on the University of Wyoming campus, and I go over to ECEC or to the lab school and just measure the height of a bunch of fifth graders, I can even randomly select the height of a bunch of fifth graders. But my methods are terrible. They're not representative, right? So I can build a confidence interval and a point estimate, but if my methods are no good, then my estimate isn't any good, right? So always, just because I've calculated something doesn't mean that it's accurate. I won't know whether it's accurate or not, but we always want to have this caveat that this is our best guess, and this is our estimated level of precision based on the data that we have, assuming we haven't violated underlying assumptions, right? And so what's helpful for this is it ends up being nice, because what we can do is we can start getting an idea of sort of how much. So this is my best guess, but how much might that vary? So we say, research suggests that people who exercise 5 hours a week or more live longer than the average US citizen. How long do individuals who exercise 5 or more hours a week typically live, right? This is an important question. Right? This is exercise and health, and we're sort of talking about a pretty intense outcome, right? Sort of life expectancy. How much, right? So I might say it's an average of 3 years plus or minus 4 years, right? I'm kind of worried about that estimate because it means that maybe I could live up to like 7 years more or a year less. I don't know, right? So starting to draw information from that interval estimate. We say the height between men and women is not 0, right? If I run a statistical test and the average height across men and women and I find a statistically significant result, this is what that tells me, is that the difference isn't 0. That's fine, but I'm probably more interested in how much, right? How much taller are men than women if I'm interested in individual differences and things along these lines. This is information that all gets rolled up into our confidence intervals, our interval estimates, that ends up making these, if we're serious about understanding something about behavior, these become hugely informative. Okay? So our confidence, who's worked with confidence intervals in undergraduate statistics and stuff? So some interval stuff, a little bit. Oftentimes, these interval estimates get identified as something to do in your undergraduate statistics class, and then you immediately forget them and just move on to hypothesis testing stuff. That's a systemic problem in terms of training, just because your confidence intervals give you so much more information than your statistical or your null hypothesis test stuff. But if we're thinking about your confidence interval, what we have is an interval estimate given some assumed level of precision, again, based on the data that we've collected and sort of assuming that we've met all of our underlying assumptions. Here we have, if we're looking at our confidence interval around the mean, we have our point estimate of the mean, we have our level of estimation here, and then we have our interval estimate, giving us a lower bound and an upper bound of values that are going to be compatible with the data that we've collected. So this is our best estimate, right, of whatever we're measuring. But based on the data that we've collected, the method that we've got, it would be reasonable to guess that this value is anywhere from 18 to 43 on this. So if we're doing a formal interpretation of confidence intervals, like a methodologically precise estimate of a confidence interval, we would say that over an infinite number of replications, if I were to calculate these intervals from all possible samples that could be drawn from this population, the confidence interval is giving you the proportion of this sort of level of estimation is giving you the proportion of intervals expected to capture the actual population value. And this is hard to wrap your head around, but it's important to recognize that confidence, right? When we're talking about confidence, this is a property of the method and not a property of the interval, okay? A lot of times what we see is someone will say there's a 95% chance that the confidence interval contains the true population parameter. Who here has heard this before? Who here has said this before? Who here has read this in statistic textbooks that say this is how you interpret a confidence interval? This is all not technically correct. If we're getting into sort of the nuts and bolts of correct interpretation of our statistical results, we can't say this because it's not accurate. We're all scientists, and sort of science isn't about like a close enough type of thing, right? We want to be precise. The problem with this is that the whole idea behind your interval estimates is taking a frequentist approach, okay? The idea, and with most of our statistical tests, taking this approach that if I were to take all, and again, so let's use height of on-campus UW students, and I'm saying of sample size 100. And if I were to calculate all possible samples of sample size 100 that I could pull from the population, and I were to calculate a confidence interval from each one of those, who knows how many number of samples I could pull, what we would say is across those replications, 95% of the interval estimates that could be generated from all possible samples would contain your actual parameter, okay? So if I were to go through and replicate a study again and again and again and again and again, what I would find is that individual confidence intervals from each one of those studies, even if it's the exact same method, the exact same population, these confidence intervals are going to jump around, okay? I've got a study with sample size 50, I do it again and again and again and again and again. The interval estimates I get for my mean value are going to jump around, and sometimes by quite a bit, right? Over the long term, 95 of those intervals that I would calculate are going to capture sort of the true population parameter, whatever that is. We don't know what it is. It's a hypothetical value, but 95% of them are going to grab that. But some of them aren't, right? We've got an interval here, we've got an interval here. These are studies. There's nothing wrong with the studies. We've just gone through and we've run a study. We've calculated a confidence interval, but these ones don't actually contain the true population parameter, okay? And so what would happen is if we say there's a 95% chance that some interval, say this interval, contains the actual population parameter, it assumes, so I'm inferring that that population parameter is a variable. Population parameter isn't a variable, it's a thing, it's a number. We don't know what it is, but it's some number out there, right? So if I get an interval of lower limit of 3.45, upper limit of 7.86, right? And I say there's a 95% chance that the true actual population parameter falls between 3.5 and 7.9, right? That's not a true statement, right? Because for that parameter, population, or for that interval, the population parameter is either in or it's not. It's 0 or 1. There's not like a chance for that parameter. Now the rub is that we don't know whether or not the parameter, the interval estimate that we've calculated is one of these ones that's actually captured our actual population parameter, or if we're one of these ones out here that's way off base. Now if we were to do, say, 50 replications of the same study, let's say you're a social psychologist and that's what you have to do to publish anything, you have to run 50 different studies, then you might start to get an understanding of whether or not any one interval starts to be weird or out of place, right? Or if we're running a meta-analysis and we're looking at aggregating a lot of different studies. But for me, as a clinical psychologist, as I run my one study, I have no way of knowing, just based on the data that I've collected, whether or not I've got one of these folks here or one of these ones out here, right? And so this is why it starts to become very, very, very important to not just know what's a significant effect and what's not a significant effect in previous research, to start to get an understanding of sort of in past research, what are the actual parameters, what are the actual values? What's the confidence limits on those values that other people have found? Where do my data fall relative to what other people have found? And then starting to think about, does my data make sense? Neiman, 1973, coverage probability is a property of a long sequence of confidence intervals computed from valid models rather than the property of any single confidence interval. And so it starts to become difficult when we're trying to communicate what this information, this confidence interval is providing. We can't just say that there's a 95% chance that this specific interval that I'm looking at, my observed interval, contains the actual population value, because I don't know, it might be off base, and the chance is actually 0, right? To the population parameter, it isn't. Like sometimes it's in here, sometimes it's not. Nope, but either it is or it isn't. So we have to be careful about how we're talking with this. Okay. Other thing to remember, we're going to get into this when we get into hypothesis testing. Remember that any confidence interval that we calculate represents a best case scenario. Anything that we do from a statistical standpoint, our validity of our estimates are completely dependent on the representativeness of our sample, our methods, making sure that we haven't violated sort of basic underlying assumptions of our model. So this interval is sort of the best representation under the best possible circumstances. If I've run a perfect study with no violations of my underlying assumptions, then yes, 95% of these intervals will capture the actual population parameter. This individual parameter, or this individual interval estimate, I really don't know. Okay? How many times would we run a perfect study where we have 0 violations of anything? None, right? So this starts to speak to the problems, sort of things we have to be very, very, very careful that we're not over-interpreting our results. There's far more variability and inconsistency, and then we want to think about it as, oh, this is the method, these are the structures, and I'm using fancy software, and so this is all perfect and good. It's not. It's a shot in the dark, and only through sort of doing this again and again and again, having a good understanding of your literature, are you able to kind of start to pull out a signal. Any individual study tells us very little about anything. Okay. Questions on sort of why saying that there's a 95% chance that sort of this interval captures the population parameter? Questions about why that is not quite right, and so what's going on with sort of the method of all this. Okay. All right, so how do we go through and interpret these? What I don't want to see in anybody's assignment ever, don't ever turn into me over an infinite number of replications, blah, blah. It's technically a correct answer, it's the methodologically correct answer, but as soon as you're talking to someone in the public about your research findings and you start talking about an infinite number of replications, their eyes are going to glaze over, they're not going to understand what the hell you're talking about, right? So what we want to do is be able to sort of come up with some ways of phrasing and interpreting confidence intervals that start to make sense from a practical standpoint to someone who's not a statistics major who understands frequent distance statistics and infinite replications and so on and so forth. Okay? So one way we might go through and interpret a confidence interval, we can say confidence interval represents a range of plausible values for whatever our parameter is, given the available data. Again, this is important, right? So this is our best guess, given the available data. We would say that values falling outside the interval we think are relatively plausible based on the data that we've collected and the underlying assumptions of the model, right? Improbable is not possible, right? And those have to be careful about those values that are falling like right on the edge. Bright line decision points are something to be avoided at all costs, right? So if my lower bound on my interval estimate is 3.22 and so my null value is 3.21, 3.21 is still pretty, it's not within my confidence interval, but it's right next to it. So functionally, it's not different, right? So wanting to be thinking about that. So we like this, right? Say the observed data are compatible with values of the parameter falling within the interval, but relatively incompatible with values falling outside the interval, right? So these are the data, so based on the data that we've collected, this is our best guess for the population parameter. If it's in the interval, pretty reasonable. Outside, not terribly, not compatible, at least based on the data that we've got. Values compatible with the data given the underlying model range from your lower estimate to your upper estimate. Lower limit provides a plausible lower bound estimate for the parameter. Upper limit is reasonable upper bound for the data, right? The margin of error reflects the largest expected error of the estimate based on the data in the underlying model, right? So this is where we get that plus or minus when we're calculating our confidence interval, referring to that as the margin of error, right? So if my confidence interval is 5 plus or minus 2 is my margin of error, right? Plus or minus 2 points on my point estimate. That's fine. We can be 95% confident that our interval includes the population parameter. No, don't want to see that one. Okay. So this, you're probably looking at this and you're like, yeah, sure. Like I don't know why you spend 5 minutes reading things off a slide to us. But people have a really hard time interpreting confidence intervals, and I don't know. Like, I don't know, what, as you were trying to get proficient in interpreting interval estimates, like, what types of things tripped you up?
Making sure you're not talking about the true value being something that might change around, like 95% of the time. The true value will lie between here, making it sound like the true value changes, because it doesn't, that was really the hardest part, was trying to make sure that what I was saying didn't come across like that.
Okay, and this is a good point. Here's a tip. When you're interpreting confidence intervals, don't try and work in like the level of estimation, like, oh, there's a 99% or there's a 95%. Forget that. Like somewhere in your interpretation, you'll indicate 95% sort of, and then the brackets in your interval estimate. I'll know then that's you communicating what interval estimate you use. For the most part, we're using 95% intervals. If you're not using 95% interval, you probably should have a good reason for using a different level, right? Part of it is like trying to get that confidence level worked in there. You don't need to do that, right? If you've indicated somewhere else in your paper, your answer that sort of basically we're calculating 95 intervals, if you're sort of putting those in there, cool. I see what level of estimation you're using. Don't worry about that. Trying to do the verbal gymnastics of working that estimation level into the words without screwing it all up and getting something like this, it's not worth it. Again, we're wanting to go through and work on interpretations that are meaningful, that go through communicating stuff to people. Okay. Any questions about sort of this or interpreting these interval estimates? I mean, at its very basic level, it ends up being pretty straightforward. Here's my best guess. Based on the data that I've collected in the underlying model, here's a lower bound. things that are compatible with the data. Here's the upper bound on things that are compatible with the data. Actually, any point estimate falling between those. If you told me this is the actual population, I'd be like, okay, that's fair enough, right? Things that are outside, not impossible, but based on the data that I've collected. Questions on this? Okay, cool. So again, thinking about this Cohen article, researcher routinely reports 95% confidence intervals, can expect over a lifetime that about 95% of those intervals will capture the parameters estimated, right? Again, just thinking about this in terms conceptually of sort of a frequentist approach. If I do this over my lifetime, about 95% of the intervals I'm reporting are going to be pretty good, but the problem is we never know for any one single individual whether we've captured it or missed it. All right. So strengths of this. So why is this important? Why might we prefer this over just identifying something as statistically significant or not significant? These interval estimates give us both our point estimate and an estimate of our expected precision, like how close or how far off, how accurate are we with this interval estimate here. Again, emphasis on how much, generally more useful than is it equal to 0, okay? I'm doing, Alicia, you're doing a treatment outcome study on PTSD, right? And you say, my treatment causes a non-zero decrease in symptoms. Are you super excited about that? If that's what I told you, and you're a clinician out in the real world, would you be super excited about that conclusion? Not really. Why?
I really wouldn't understand what that means, first off.
So basically I'm saying that the expected change in symptoms, the expected reduction of change in symptoms is not 0.
But you don't know what that is.
Yeah, right, maybe it's 1 point on some whatever scale. Is that super helpful to my client? Probably not, right? So it's statistically significant, but like, I don't know what the practical significance is, right? With our interval estimates, we're getting sort of a better sense for the magnitude of effect, both on our sort of on the best case scenario, or sort of lower bound, upper bound, and then we're getting an index of precision. We can see how tight or wide that confidence interval is. Do we want narrow interval estimates or wide interval estimates? Which one of those are better? What do you think, Chris? Narrow. Why?
Because that presumes that you're like putting in more on what you're actually looking at.
Yeah, right. If I say, so looking at the difference between clinic or professionals who have a master's degree in psychology or PhD in psychology, I'm saying that they make $15,000 more a year. $15,000 more a year than master's levels, and that sort of that difference ranges anywhere from $50 a year to $40,000 a year.
It's not a great estimate.
It's not a great estimate, right? Like I 15,000 more is, or maybe it's $50 more a year. That doesn't seem like it's worth the extra 3 years of headache and all that stuff, right? So we're wanting to go through and thinking about sort of how precise are our guesses with this, okay? Our interval estimates are going to provide more accurate and meaningful perspectives on the effects that we're seeing in the literature. We're going to talk about this. I am reading a paper, right, and I see, oh, it's a statistically significant effect. How big is the effect, right? How much of a difference am I seeing between participants who have received the manipulation and who haven't, right? And then how close is that lower bound of the null estimate? If my null hypothesis is there's 0 difference, the lower bound on that is, well, 0.0001 to something. I'm not going to be super excited. I mean, yeah, technically it eked across the 0.05 line, but based on the data I've collected, it says that like the actual difference between the people who've gotten the manipulation and not could be 1/10,000th of a point along whatever it is I'm measuring. That's not overly compelling, right? We don't get that in our significance test, but we do get that with our interval estimates. Also providing a much better assessment of how comparable study effects are or findings are across the studies. Our interval estimates is the heart and soul of our meta-analytic procedures, right? If we're looking at significance test, whether or not something has been, we have a statistically significant finding or an effect that's been found to be statistically significant or not statistically significant. This is a terrible, terrible means of sort of assessing whether or not results of different studies are comparable or not comparable, right? Because if I get a P of 0.049, sort of right here, and I can get to statistical significance, it's 0.051, then I say it's not statistically significant. We say, oh, those are completely different out, so you replicated or you didn't. When in fact, the point estimates might be super, super close. The bounds of that sort of just might be just barely different from one another. So these interval estimates are a much better way of going through and saying, all right, Chris found this in his study. I went through, his was a statistically significant effect. I went through, I didn't find a statistically significant effect. But what's his point estimate? How precise is his estimate? Where's mine fall? Actually see the intervals overlap a whole lot. Functionally, we found the exact same thing, even though we were able to claim statistical significance and I wasn't, right? And so doing a much better job of being able to synthesize literature and see, sort of, are we finding the same thing? Are we kind of converging on a common theme here, or are people sort of way off in all over the place? Okay. So again, from this Wilkinson paper, again, just advocating for sort of confidence or interval estimation as being really our best reporting strategy or our best practice approach. I've been going through this, so I don't spend a lot of time. The ASA came out with new recommendations in terms of best practice for statistical hypothesis testing in science and things like that. We're going to talk about some of the limitations, and people have been talking about for years and years all the different problems with the way we approach science, right? And so trying something new this semester, going to go through and try to push you towards best practice approaches to thinking about and synthesizing information, interpreting things to help us get out of this rut of doing things that are terrible just because we've been doing it for years and years. Doesn't mean we should probably continue to keep doing it this way. Okay. So some other considerations here. This is hard for us in psychology, right? Because sometimes the things that we're looking at are some theoretical thing, right? Like, oh, my model says that different levels of this should impact that. And so what are the actual practical interpretations of this? Maybe nothing at all, right? So thinking about sort of conceptual practical implications of lower and upper bound estimates starts to become more important than if I'm just like, say, an economist, I'm looking at like sort of dollar amounts in people's income, or if I'm a health psychologist, I'm looking at sort of blood pressure levels over sort of years of longevity or things along those lines. But we should always still keep in the back of our mind thinking about, with our interval estimates, what are the implications of the upper and lower bound limits of that interval? So sadly, if I have sort of an upper bound interval and this is a lower bound interval, are both of those upper and lower bound intervals reasonable estimates for whatever I'm looking at in that interval? Well, it does depend based on the data and sort of the, make sure I haven't violated this. Let's say I've conducted a perfect study. Lower and upper bound, both reasonable estimates of what this population parameter could be.
Yeah.
Yeah, right? So I should be thinking about what does it mean if the parameter is actually at the lower end? And what does it mean if the parameter is actually at the upper end, right? And so it starts to become easier if I've got a real narrow estimate and there's not a lot of distance between those. But if I got super wide distance, what would it mean if the population parameter actually is on the lower end? What would it mean if it's on the upper end? If that lower end of my interval estimate is like right next door to some practical null value that sort of is functionally meaningless, how confident are we that we've actually identified something that's useful in terms of moving forward with science? You know, if I've got a really wide estimate, so like, oh, this could be nothing at all, or it could be something massive, right? How informative is that? It suggests that our data is actually, our study is actually pretty inconclusive on whether or not we've actually detected anything, right? So thinking about practically what does this mean, and incorporating that into our sort of inferences that we're drawing from our research. And always, always, always remember that our estimates are only as good as our methods. There's a a lot of discussion in terms of teaching statistics classes and having those be taught separate from methodology classes. In actual fact, the two are so intertwined. You can't really talk about, I can't talk about statistics and the accuracy of my inferences if I don't know anything about the methods. Again, our best, our mathematical, our statistical models are based on mathematical ideas. In the best case scenario, assuming no things have ever gone wrong, I've gone through and my measures are perfectly valid, and I have zero error in terms of my measurements, and my distributions are all exactly what they should be, and my sample is random, and my sample is perfectly representative, then yeah, this is what's going on. But the actual fact is we can't ever achieve all that stuff, and so we need to be thinking about sort of what are the implications. So I didn't have a random sample. Is this a big deal or is it a not big deal, right? My sample isn't representative. So who's my sample representative of? I have various weird things going on in my data, so violations of my statistical assumptions. Are these violations that are things that I can reasonably sort of say it's probably not going to be a big deal, or are these things going to start to screw around with the results that I get, right? And so if we're thinking about evaluating data and evaluating people's research, we can't gather any type of reasonable conclusions unless we're taking a hard and critical look at both sort of what they've done in the study, whether or not that makes sense, and then also comparing that against existing evidence, right? Our tendency in our science is to go through it, and I'm writing an introduction and I say, well, CJ found this, and Tamara found this at a statistical level, and so then I'm going to go through and do this. It's functionally contains zero information, right? That means that CJ found something that wasn't exactly equal to zero, and Tamara found something that's exactly equal to zero. I don't know how many other studies have not found anything even close, even though they've tried, right? I don't know how big those effects are, or how small those effects are, and so we can't evaluate research without some knowledge of existing things and being able to put that into context, okay? Again, another thing too, think about the imprecision of this, right? So our measures of precision are imprecise, right? Here's the lower bound, here's the upper bound, but again, you can't take those upper and lower bounds super literally. They're not hard, bright lines. As we go through, and if we were to replicate even with the same exact method, the same exact population, we're still going to see that interval jump around. Our best case scenario is it stays pretty close, but the specific upper or lower bound that I got from my study is not going to be the identical upper or lower bound study that I got in the next replication, and so we want to be careful that we're not over-interpreting these limits by too much. Okay, so let's do this. Watching you so very closely. Also, I don't know, bonus points for anybody who can find a picture of Sting in a police hat. And I was trying to do that, and I tried to put a police hat on Sting, you know, watching. I don't know. It seems implausible that there's nowhere on the internet a picture of Sting in a police hat, but I don't know, I couldn't find one. All right, so calculation of our confidence intervals. 3 pieces of information. We need, if we're calculating confidence intervals around the mean, we need our sample mean, this is our point estimate. We need our standard measure of standard error, and then we need, for what we're going to be doing today, a z-value for our corresponding to our chosen level of estimation. Standard error, in general, if you don't ever know the answer to a question I'm asking you, just shout standard error. It's like guessing someone's name in the department is Chris. Like you might not be right all the time, but statistically it's a pretty decent guess. Our standard error, and we'll talk about this in the next set of slides, giving you an index of how much of a difference expected from one replication sample to the next. Okay, so I say the mean.
Got it.
What's it? Did you find one?
Yeah.
God damn.
I gotta get back.
Is that? Yeah, it is.
One second.
I don't like fonts.
Do you want me to send it to you?
Yeah. I don't know. I guess I'm not Googling the right things. This Also, yeah, I'm probably on several watch lists for trying to find stuff to post into slides. And like, what about this? I'm like, oh, yikes, that's not what I wanted. I was terribly savvy in that sense. Okay, back to standard error. So let's go through, and let's say I want to, again, measure the average height of students on campus, right? And I'm going to go through and I have a sample of 50 students that I go through and take. Even if that sample is random, how much across individual samples am I expecting for that mean estimate to jump around, right? If I've got a large standard error, I'm going to have sort of big differences. I might sort of jump around by 3 to 5 inches. If I've got a really good sample, a really large sample, sort of the amount that my best guess of the mean might jump around just sort of a little bit, right? So again, thinking about standard error as the expected difference across whatever we're measuring from one replication to the next. You can also think about how this standard error is a measure of how well my sample mean, in this case, is going to be representative of the population mean. Okay? So standard error here is based on your population standard deviation, because we're still working with z-scores. Population standard deviation over the square root of your sample size. Okay? So again, primary influences on your standard error. What happens, Alicia, as my standard deviation of my population increases? What happens to my standard error? So all things being held equal, what happens if the standard deviation of my population increases? What does that do to my standard error?
Increase.
It makes it bigger, right? What happens to my standard error as my sample size increases? It goes down, right? So the more people we have in our sample, we see the standard error drive down. The more people we have in our samples, the less we expect this statistic to be jumping around across replications. Okay? Does this make sense conceptually? Yeah. Why is that, Tamara?
Because we're changing the numerator denominator.
Yeah. Okay. Yeah. The math makes sense. Conceptually, why does this make sense? If we're sort of thinking about why would we expect less variability on our estimates of the mean with larger samples as opposed to smaller samples?
We're getting like more representation.
Yeah, right. As we start to get larger samples, if we're doing this correctly, we're getting a more representative estimate of the population, and so we're expecting that to jump around a whole lot less. Good question.
Increase the N, increase the power.
Yep, yep. And so when you go through and do that, so you're jumping ahead into some power stuff like that, but
My friend.
was it
My friend always says that, so.
increase N?
Increase the N, increase the power.
Yeah, that's good, right?
She has a t-shirt that says that.
Okay, so either way, you got, it's probably that's a succinct way to answer maybe a question on, a problem set question, all right? So again, can't emphasize enough, like, we're gonna talk about standard error more, but standard error is at the center of any of your inferential statistic tests. If you're gonna test something and run a hypothesis test on it, you have to have a standard error. So knowing what your standard error is, what it means conceptually, and the types of things that impact it, is gonna be super, super important. Okay. So, confidence interval. So we've got our sample mean, our standard error, and then what we need is our z-value if we're working with a z-distribution for a chosen level of estimation. If I'm wanting to calculate a 90% interval, again, this would be mathematically, we're saying over an infinite number of replications, 90% of the intervals that we could calculate would capture the population parameter. 95% interval associated with a z-value of 1.96, 99% interval z 2.58. So, CJ, what's happening as my chosen level of estimation increases? What does this do to my interval estimate?
Also increases?
Yeah, it makes the width of that interval increase, right? And this is just straight up probability stuff, right? If I wanted a 100% confidence interval, I just say this parameter lies anywhere from -infinity to infinity, right? then yeah, that's how it's going to capture it, right? At a 90% interval, I'm sort of saying, okay, so kind of this interval here, we've got a pretty decent job, expectation that sort of most of these are going to catch the actual population parameter. If I jump up to 95% confidence, so it gets a little bit larger, right? Because I'm trying to capture more. 99 gets a little bit larger, right? And so just knee-jerk reaction is just to look at the formula and just plug stuff into the formula and take it on faith that that's doing what it's supposed to do. But with applied stuff, it's always good to actually look at that math and say, okay, what's going on? How does this make sense? How do I understand it? It's just going to be a lot easier to identify when you're making mistakes, and so bring strong interpretations on the stuff that you're trying to work with. Okay. So any questions up to this point? Yeah.
This might not make too much sense, but if you have a measure that consists of like 4 questions versus one that has like 100, does that play a role in confidence intervals at all?
It could. Now we know that like short versions, short measures generally are less reliable than longer ones, right? So if I get more questions, I'm kind of getting closer in on what I'm trying to look at versus a shorter measure. So what I might expect is that my relative variability of the short measure is bigger than the relative variability of my longer measure, right? I might expect with the longer measure, I'm getting less variability across replications or across test retest. It's honing in a lot better, and so we get less variability. And if I have less variability, then this is going to be smaller, right? Which is going to decrease my standard error. But in general, there's oftentimes not. Can we do anything about the population variability? No. I mean, it is what it is. We can't do anything to impact this necessarily. We can do something about the sample size, right? We can give an infinite number of resources. We can always crank up the sample size, right? So this is going to be the more efficient way to go through and drive down standard error. But we can, if I'm talking about the variability of the long measure, is this. The variability of the short measure is this. I'd probably be more concerned in that situation about the ability of my estimates more so than the standard error of my tests. I mean, it's going to make a difference, but probably not huge, and you just maybe collect a few more people, and that's probably going to offset that. My concern would be more along the lines of, is whatever is the assessment that I'm giving an accurate and reliable measure of what it is that I'm trying to capture? That's probably the bigger thing I would be concerned about in that scenario. Other questions about this? Okay, cool. All right. So just a quick example here. So we've got, I like contrived examples that don't map on anything that anybody cares about. So we've got a local librarian has claimed on average that books are 20 years old. New librarian is interested in re-estimating the age of the library's books. Randomly selects 150 books and records the publication date. The mean age of the books in the sample is 23.8 years with a variance of 67.5. Okay, so if we're going to go through what we want to do, first calculate the point estimate of the true age of our books. Chris, what's the point estimate of the true age of our books?
Is it 23.8?
Yeah, it is. How did you, that was fast. How did you do that? How did you get that?
Because the mean is the point estimate.
Yeah, right.
Okay.
Based on our sample, this is our best guess, right? Now, do we think that the actual age of the population of books in the library actually is 23.8?
No.
No.
That's our best guess.
We know it's probably not, that's not going to be exactly what it is, but it's our best guess, right? With the data that we have, this is our best guess. So what we want to do now is calculate a 95% confidence interval for the true age of the book, of the books. So we've got our point estimate, a mean here. Lauren, will you drop down to my office and grab a couple of good markers instead of terrible markers?
Any color preferences?
No. Yellow.
Yeah. There you got it.
All right. So we need to want to calculate a 95% confidence interval here. So we've got 150 books, right? And then we've got a variance of points equals 67.5. Okay, and my null here is the actual age is 20 years. Okay, so someone help me out. I want to calculate a confidence interval for the actual, based on the data that I've collected, the actual age of the books. What do I need to do first? Calculate the standard error. Okay, so my standard error is going to be, well, we do. Can I use this number? My standard error? Well, I can. I just need to do something with it, right? Chris, you're shaking your head. What don't I like about this? If we're going to straight plug it into the previous one.
It's the variance, not the standard
It's
deviation.
the variance, not the standard deviation, right? So I could do two things. I could take the square root of that and get my standard deviation, or I can just overall go 67.5 over my sample size 150. So mathematically, it is the same things. I could take the square root of my variance or my standard deviation divided by the square root of my sample size, or I can just do it all. So it doesn't matter. It's mathematically, it's the same thing. Someone tell me what I get. What's my standard error here? What you got, TJ?
Figuring it out. I think it's 2.347. I don't know how far you want to go there, but
Is that like 3 decimal places? 2.347. Is that what other people got? Is that right?
I got like 154.
Yeah, that's.
0.054. All right. Where do we go wrong? Let's
So
see.
first we take the square root of 67.5 and then divide by 150.
Yeah. So we go. Is it an order of operations? 67.5. 150 divide. So we're at 1671. 67.5, 150, divide. Awesome. Thank you. All right, yeah, I'm good. I'm getting 0.671.
that's what I got. That's what I got.
Okay. So, what,
So I first took the square root of 67.5
okay,
and then divided that by 150.
okay, you gotta take the square root of 150,
Oh, okay.
right? So, and this is just sort of math stuff, so we said standard error is gonna be your variance over the square root of it, okay? So, but if I have my variance, then I just take that divided by that, take the square root of the whole thing, and then we're good, so. All right, good on that? Okay, cool. So we've got our standard error. What do we need to do now?
Multiply it by 1.96.
Yeah, and why are we saying 1.96?
That is the for 95% interval.
Yep, and why is that the Z for the 95% interval?
Because you said so?
Because oh, yes. In general, because Josh said so is a terrible, terrible justification for anything. Do not use this in your meetings with any of your advisors, except for you, because you said so. That's fine. Don't argue with your advisor. Say Josh said to do it this way. That's not a strong rationale for anything. What's special about 1.96? Why is that the level for our 95% interval estimate?
Corresponds to our Z table, which follows a normal distribution, and that's the Z score for that confidence interval.
Yeah. So yep, you're on the right track. So at 1.96, if you pull up your Z table, what percentage of the curve is left in the tail? 2.5, right? And so if we take 1.96, negative 1.96 in that Z table there, we've got 2.5% of the distribution in the top tail, 2.5% of the distribution in the other tail, plus or minus 1.96, that captures that 95% of the body of the table there, right? Same thing if we drop down to a 90% confidence interval, that's 1.65, right? That captures the middle, the 90%, 99, 2.57. What's up? 2.58, that's capturing 99% of the body. So what this is doing is just corresponding back to that unit normal table and sort of looking at sort of how much is in the tails, right? So we've got now everything we need to calculate our confidence interval. We've got point estimate, 23.8. We're going to say plus or minus 1.96 times 0.671, okay? And what do we call this value right here? Can someone multiply 1.96 by 0.671? Tell me what you get.
1.29.
1.29? Is that right?
1.31.
I got 1.315.
What's that?
1.315.
1.315.
It's called 1.2.
Okay.
I didn't round, I just like left it in there.
Oh, okay. 0.671. So this starts to become, you see, yeah, 1.315. So yeah, 1.3. Okay. And so I'll tell you right now, sort of like again, when you're running your calculations, take things out to 3 decimal places, because this is with decimals, it'll start to jump things around, and then Laura and I have to sit down and try and figure out if you sort of made a small error somewhere in the calculations, or if it's just a rounding issue. So we'll call this good here. Right here, I just told you to round to 3 decimal places, and I didn't. So there. Okay. What is this? What do we call this? I kind of snuck it in. So anybody catch?
Standard error.
Not okay. So this is my standard error. Close. Not standard error. Margin of error. Margin of error, right? So what we can do is in our interpretations, right? I could say that reasonable estimates, sort of age of the book falling above plus or minus 1.32 are reasonable estimates and things like that, right? So this is just our margin of error right here. Basically, you think about this as like our tolerance, right? Here's my point estimate, here's the tolerance, here's the margin of error on this, okay? So, what is my 95% confidence interval here? What's my lower bound estimate based on the data that I've collected?
22.485.
22.485, I'll say 49, just for this, we'll round it to 2. All right, what's my upper estimate, my upper limit? What do you got tomorrow?
I didn't.
25 point what?
115.
115. Okay. So there we go. So what we've done now is we've calculated our interval estimate for, based on the data we've collected, for the actual age of books within the library here. Okay? People kind of see the math. All right. The one thing you want to do, and this will screw you up, the z-score that you're putting in here, this is the z-score that you calculated based on your confidence level, not your any test statistic that you'd be running. Like, so this is, when we get into hypothesis testing, this is always, the z-score for your confidence interval is always, if you're using z-scores, it's going to be 196, it's going to be 1.65, or it's going to be 2.58. Really. Don't plug your actual test statistic into there. That'll get you all screwed up. Okay. All right. So what we're going to do then, so the last year wanted to provide an interpretation for this confidence interval. Chris, you want to give this a shot?
All right.
Well, it seems unlikely that the former librarian's previous estimation was correct of 20.
Okay, that's beautiful. Why do you say that?
Because it does not lie within our confidence interval.
Right. Now, is that estimate of 20, is it possible?
Yes.
It's possible. Just based on the data that we've collected, it seems not probable, right? So, good. So we would say, in terms of answering the question, it seems like these, based on the data that we've collected, that the average age of books in the library are older than what were estimated by the previous librarian. What about for this interval estimate? Can you give me a conceptual interpretation of what we've got going on there?
All right. Based on the data we collected, it seems probable that the mean is in between the 22.49 and 25.12.
Mm-hmm. Or what?
Our upper and lower bounds
Of what?
of our confidence interval.
Yeah, well, what are we measuring here?
Oh, the age of the books.
There we go. Okay. So when you're going through and interpreting these interval estimates, wanting to always remember, like, again, we're not just running numbers for the hey-ho heck of it, right? We're trying to infer something about a real thing, and to the extent that we can remember that and sort of frame our interpretations within the context of sort of the actual question at hand, it's going to help you solidify and understand, so from a practical standpoint, what this means. So I would say, so based on the data that we've collected and assuming the underlying, based on the underlying assumptions of our model, I would say that a reasonable lower bound estimate for the true age of the population books in this library, somewhere between 22.5 and 25.1 years, right? Given the previous estimate of 20 years, looks like that's going to be an underestimate. It's not impossible, but it doesn't appear to be plausible based on the data. Nick, what are we saying? If we look at this interval, are we happy with this interval? In terms of our level of precision?
I guess in the perspective of all the books, that would probably be in a library. That's pretty close.
It's pretty close, yeah. And so going through, and I mean, so plus or minus a little over a year in terms of the accuracy on, that's pretty good, right? What contributed to sort of the precision of our estimate in sort of this case here?
We had a pretty large sample size.
Yeah,
of books.
we're right on track. Sample size, I mean, by the time we're getting up to, for psychologists, 150 is a pretty decent size sample. If we're talking about, I've got friends over in econ, and they're samples of like 5 million observations of sort of tax returns or something like that. And they're not too excited. But for us, it's a decent size sample, and it's contributing to a pretty precise estimate of what we've got going on here, right? So we would say, and so I could look at this and I could say that estimates of the true the age of the population books in this library are compatible with values ranging from 22.5 to 25.1, assuming sort of underlying statistical assumptions of the model, right? Based on the data that we've collected, we expect our point estimate of the population age of the books 23.8 with a margin of error plus or minus 1.3 years, right? There's just a lot of different ways that you can go through and describe this, and what I'm going to do as we move forward with this is to encourage you all to sort of use different ways, play around with different ways of talking about this in ways that make sense for the given problem. This is going to help you sort of get more flexible. You could, if you want to, have just your one stock phrase and cut and paste it into things, but it's going to be harder to understand exactly what's going on as opposed to if you're playing around with different interpretations here. Okay. So questions on how we went through, got that confidence interval, things that we're taking from it, anything along those lines. All right. So we can do this again. We say a researcher interested in the Flynn effect would like to know what the current average of a score would be for an IQ test developed in 1980. Random sample of 120 people were tested. Scores had a mean value of 107 with a standard deviation of 12. Population mean in 1980 was 100. Okay. So can someone tell me what the Flynn effect is and what this question was trying to get at? Yeah.
I don't know, but just based on the context of the question, would it be that over the course of time, people improve, like populations improve on IQ tests?
Yep, exactly. As we're going through and sort of looking at the evaluation of intellectual ability, we see an up creep. And so if we norming this, what ends up happening is if we set the mean when we norm it at 100, over time it starts to creep up, right? And so this is known as the Flynn effect. And so we've got a test that was developed in 1980, and in, let's say, 2019, we take 100 people and find the mean is 107, with standard deviation of 12. What's the expected mean is 100 in 1980. What was the expected standard deviation? 15, right? So this is just, and so what we're seeing is we're creeping up. But what we want to know is we want to calculate an estimate for the current population on the old test, right? So what do people in 2019, what is their average score? We want to calculate a 99% interval for the true population mean in 2019, and then move on and provide interpretations and things along those lines, okay? So we won't do this on the board here. We've gone through it just to save some time, but our point estimate of current population score, this is just the mean, right? Again, it's our best guess. So we're guessing that it's 107. We calculated our standard error here. We've got a 99% confidence interval, so our level of estimation corresponds with a z of 2.58. Here's my standard error. Here's my interval estimate. Here's my margin of error, right? So here, different ways you might frame this in terms of thinking about it. Based on the available data, plausible values of the average score in the 1980 exam, remembers the current population range from 104.2 to 109.8, assuming the normal distribution of scores, right? What did we, what's going on in here, sort of in this interpretation? So what information am I getting at? So I've got the upper bound, I've got the lower bound, right? And I'm also important in this one, I'm going to beat you guys up on, and so as we're moving through, identifying what the population is that we're referring to, and so what we're actually measuring, right? So if you just give me an interpretation that says the upper and lower bound, or upper and lower bound estimates for this sample are X and Y, I'm probably going to ding you on that, right? Because you're not telling me, one, what you're studying, or what we're measuring, two, what the population is intended to get at. Because remember, this whole endeavor is to infer something about some population parameter that is unknowable, right? And so wanting to know what population we're talking about. You know, we'd say data collected in the study suggested average scores on the exam falling to be below 104.2 or 109.8, not compatible with estimates of performance of the current population. Suggests an average score of 107, with estimates indicating expected error of estimation plus or minus 2.8 points. Estimates of performance on the 1980 exam compatible with these data range from 104.2 to 109.8, assuming normal distribution of scores. This is just different ways of saying the same thing, wanting you to feel comfortable and flexible in sort of changing how you're going to go through, communicate this stuff, so it doesn't feel like you're just robotically saying the same things, right? I can teach you how to say these words and you can memorize scripts, but it doesn't facilitate understanding of actually what's going on. Okay? So again, if we're thinking about general conclusions, we see average performance on the tests seems fairly precise, as Nick pointed out. Again, assuming we have a representative sample and a normal distribution of scores, larger population of adults. So sort of thinking about our underlying assumptions here, we might conclude that results appear consistent with those expected for the hypothesized Flynn effect. Although what we should consider is practical impact of possible deviation of 4.2 points above the expected mean of 100, right? So this starts to get into your practical impact. So we see, yeah, it looks like there's been possible up creep. As Chris pointed out, that a score of a 100 on this in the current population doesn't seem plausible based on the data that we've collected. It looks like we have a difference of, again, our point estimate is we're about 7 points above the mean, but the lower bound on this, 104.2, suggests sort of a minimum increase based on our data of about just a little over 4 points. So what we might want to ask is this meaningful, right? Let's say our test is drifted, so the actual population mean today on this exam, it's about 4 points higher than it once was. Is this important? I don't know, Alicia, you had some assessment experience in doing some of this stuff. Is a 4-point difference important?
Not if you're looking at the standing scores. So like if you're doing like the 15,
Mhm.
deviation of 15,
Mhm.
because then that would fall within that.
Yep.
So then that, you're still within that one standard deviation.
Yeah.
So
So we're still within kind of what is generally expected, right? And again, sort of at least we've got about a 4.2 increase. At most, close to a 10-point increase. And 10-point increase, that's maybe starting to get sort of more concerning. And so wanting to take both of these things into consideration. But if on the low end, just a little over a 4-point increase is about what we would expect in terms of the shift, we might not be too worried about that. Like, it's sort of kind of creeping up a little bit. I asked Tara about this a little bit, and she's like, yeah, the 4 points is not that huge. Well, what happens if we start worrying about whether or not people start to meet criteria for intellectual disabilities and services and stuff like that? Now, all of a sudden, if just on average, the set is, so the people are actually scoring about a little over 4 points higher, and you get someone who's, if the cutoff is 75, and now you've got someone who's 77, and someone who doesn't understand these tests say, nope, this person doesn't meet because they've scored too high on this score. Well, now all of a sudden that 4-point difference does start to make a difference, right? Because if the practical impact of these tests and what they're used for start to have big impacts on people's lives, or let's say I'm on death row because I was involved in a sort of murder and I have some pretty significant intellectual disabilities, but I'm 2 points higher than the cutoff for sort of whatever this is. Now all of a sudden this creep up starts to make more of a difference, right? And so these are the types of things when we're thinking about our statistical analyses, what's the practical impact? Obviously, a 10-point is sort of at most, so our best guess is, is about a 7-point increase. That's kind of big. At most, about a 10-point, that's certainly concerning. But what about this lower limit? At least a 4-point increase in the general grand scheme of things, probably not a huge deal, but on margins, if we're looking at what we're actually using this for, now all of a sudden this maybe starts to become a big difference, right? Because people don't understand these tests, and we're using bright line cutoffs, and now I'm a point above what would enable me to get services, but I'm using an old test, and everything's kind of drifted up, right? So these are the types of things we want to be thinking about, as just opposed to saying, yeah, there's a reliable difference, it looks like it's increased. By how much? And so what are the implications of that? Questions on this? All right. So, some additional things to be thinking about are confidence intervals. If we're talking about the age of the books, our point estimate is somewhere right here, right? And this is our 95% confidence interval, ranging from sort of lower limit to upper limit. But always remember that not all values within my interval are equally plausible, right? We're in general saying that all values within that interval are going to be compatible with the data, right? Sort of based on our level of estimation. But am I more likely, if I had to, CJ, if you had to sort of throw down a $100 bet on whether or not the point estimate is going to be this, or the actual parameter is going to be this value or that value, which one are you going to bet on?
First value.
First value, right? This starts to become, as we start to get towards the end of that interval estimate, those values become increasingly less likely until we hit some point and then we're saying, okay, now it's out of the bounds, and so now these data aren't compatible. But if I have something that's right here versus right there, those aren't categorically different, right? So important to start thinking about these things in terms of sort of continuous evidence and not bright lines. So yeah, we have to, I guess, draw a line somewhere, and our level of estimation says that this is kind of where we're at, but still, this is still the best estimate that I have, right? Same thing with my IQ scores. I'm guessing that sort of scores on the current population in this test that was scored, or that was normed in 1980, is about right here. This is my best guess. Any value falling within this interval, I say, are consistent or compatible with the data that we've collected. But these scores at the higher end start to get increasingly unlikely, much more likely to have something there in the middle, right? So it's not just a flat distribution, so somehow magically, so we've got everything is equally likely across this interval, and then we tip it to things that are now unlikely. So we're still seeing this natural distribution of scores. Okay, people kind of seeing what's going on with that. All right. So we can also go through and calculate sort of multiple intervals for different tests. Here, we've got an example where we have lecithin, a chemical protein, or a chemical found in protein-rich food. We're expecting it to improve memory. Sample of 10 newborn rats are giving a normal diet containing lecithin, while 7 rats in a separate sample giving a diet with no lecithin. Both samples giving a memory test in adulthood. So these are like rat IQ tests. Sample data for the lecithin sample, no lecithin sample. Performance in memory. Performance on the memory assessment is assumed to follow a normal distribution in this strain of rat. Scores deviate by 7 or more points, interpreted as having practical difference based on prior psychometric research. Okay, so what we're doing here, we're trying to give you some context to say this is about the magnitude of difference where we would start to say, okay, yeah, this is kind of an important thing, right? So again, we calculate the point estimate, calculate 95% confidence interval, write interpretation. Okay, again, I've just gone through and done this. I mean, this is all pretty straightforward. You kind of see what's going on here. We've got our control group. This is going to be rats that have a normal diet. This is the group that's going to have no lecithin in their diet. We've got confidence interval on memory score for the control rats, and confidence interval for the rats with no lecithin in their diet. Interpretation here, we might say this is just wide, we'll give you one here, but population estimates for the average memory score of rats receiving standard levels of dietary lecithin 20.2 to 29.8, point estimate 25, point estimate of memory traits in rats with no dietary lecithin was 33, with population values ranging from 28.5 to, or population values from 28.5, 37.5 compatible with the data given the underlying model. Okay, so again, as I'm interpreting this, I'm trying to sort of make sure that we're noting what the population what populations I'm referring to. That these are data that are sort of based on sort of the underlying model, things along these lines. Okay, so we can give that interpretation, but then if we're thinking about practical impact, right, things that we want to be thinking about. I say precision of these estimates is poor, largely due to the small number of observations, right? If I'm looking at sort of the width of my intervals here, they're pretty big, right? Because I've got sample sizes of 10 and 7. If I got sample sizes of 10 and 7, my estimated precision of my estimation is really, really terrible. It could be anything from here, anything from here, right? We're concerned about how confident we can be in that point estimate. Our point estimate isn't very good. Okay? The point estimates of memory scores fall outside confidence bands of the opposing groups. If we go through and take a look at these estimates here, you might see this here, and then something like that, right? So my control group, so the point estimate for my no lecithin group of 33 doesn't fall in the confidence interval for my control group, right? 20 to 29, 33 is out here. Point estimate for my control is 25, falls outside the confidence band here, right? So it looks like we sort of have missed some of that, but we do have some overlap here in the upper and lower limits, right? So it's possible. Is it possible that these two samples have equal memory scores? Yeah, it's possible, right? If you told me that these two populations of rats, the hypothetical, sort of the actual population of rats and the hypothetical rats that don't have lecithin in their diet, if you said that those population values are actually equal, yeah, I mean, maybe not terribly likely, but it's consistent with the data that we've collected, right? And so we're seeing that data are compatible with differences ranging 1.3 higher on the less than restricted rats, 17.3 points higher for, sort of ranging from 1.3 higher for the rats with no lecithin to 17.3 higher for the rats with normal lecithin, right? So this is looking at comparing the lower limit here and the upper limit here to the lower limit here and the upper limit here. This is the range of differences that would be supported by these data. Data support the possibility of no meaningful difference in population scores. If we're saying population differences greater than or equal to 7, right? These data are consistent with scores suggesting no meaningful difference across the population, all the way to possibility of considerable deficits in the lecithin restricted rats, right? What's important here is this is in the opposite direction. If we go back to when we read the original hypotheses, we're saying that lecithin is expected to improve memory, right? But if we actually look at our means, we see that the rats that don't have any lecithin in their diet are scoring on average higher than the ones who do, right? This is in the complete opposite direction of what we had hypothesized. And so this starts to become important when we're going through and we're trying to interpret things to make sure that we're not just saying, oh, that there are differences, or this is the mean, that's the mean. Think about how it relates, right? This is actually in the opposite direction. So that would probably be something to note here, right? So we say, while intriguing, additional data is needed to address potential relation between lecithin and memory performance in laboratory rats. Close examination of the methods in this study are also warranted, given that things are in the opposite ends of the thing, right? So basically, these data are not terribly conclusive, right? And why, Nick? What's the big driver as to why these results are probably not super conclusive?
Well, one, there's some overlap between these confidence intervals, and also because of the range of those intervals, so they're not entirely different because of the overlap, and also because the original hypothesis was saying that there was the opposite prediction that lecithin was going to improve memory, but we saw the opposite. So it's pretty convincing that it's.
Yeah. And what's Chris?
Low end.
Low end. Yeah. We've got really, really small sample studies here, and we have to be extremely careful about making overgeneralized conclusions about really, really small sample studies, right? So between all of this, we've got small samples that are contributing to pretty wide confidence intervals. We've got effects going in the opposite direction. Now, if we actually ran a 2-sample test here, we might actually find that we have a statistically significant effect in the opposite direction, and maybe we get super excited about that, right? But I don't know, the other thing too, if we take a look at the practical difference, this is anything, if our practical difference is, if I were to find a difference, a reliable difference between these two groups of 3 points on the memory test, do I care about that? No? Why not, Siley? Yeah.
Could you repeat the question?
Yeah, so if I found that these two groups differed by an average of 3 points, do I care about that?
It's too close.
Yeah, it's too close. We've said, based on previous research, that I need to see about 7 points before I'm gonna get too excited about any of this stuff, right? Now, if it was just, like 0, if any non-zero value was meaningful, then maybe I might sort of be more excited. But really, if it's not at least 7 points, then like I really don't care, right? And so between the small sample, the imprecision, things going on in the opposite direction, we really can't tell a whole lot from this. We would need to do this again with a much larger, we would need to collect a much more data in order to say anything meaningful about the stuff that's going on here. Questions about sort of how we've gone through and put this stuff together. Okay, so as we're going through, I'm going to try with our assignments and things this year to try and provide Because again, a lot of my examples are trauma stuff, just because that's the data I have, but you don't have background in trauma. They're trying to go through and sort of work in some background information to give you some basis for evaluating the data that we have. And I'll probably just make a bunch of stuff up, but at least trying to give you a sense for, as you're going through and conducting your own research, how important it is to have a good sense for what the previous research suggests, trying to get a sense for what would constitute a meaningful difference or a meaningful effect, how do my data relate to that, and trying to incorporate this into sort of come on. All right, guidelines for comparing confidence intervals. So we talked about how some confidence intervals in this last example had kind of overlapped. Cumming and Fitch have a really, really good article that talks about confidence intervals and how to eyeball, at least from a group-based difference, if you see overlapping in confidence intervals. Again, if you've got a reasonably large sample and your margin of error is no greater than about 50% overlap, generally that's going to be consistent with a significant difference, or a difference between the groups less than p equal 0.05. If there's no overlap in the confidence difference between groups design, sort of consistent with a difference p less than 0.01. We're not going to go through all of that. I think they do a pretty good job of outlining it. But this is, I think, a really nice article. One, for getting comfortable with interval estimation, and then two, recognizing how we can go through, if we understand kind of what's going on with these intervals, how we can go through and start to draw inferences from research that might not have given us the tests that we wanted to have, because they probably maybe weren't sort of central to their research question, but we can still go through and draw information and make inferences based on the information provided in comparison to interval estimate stuff. So do make sure that you go through, do that closer, you can understand exactly how all that stuff is working out. All right, let's take a break. Feeling all right? Feeling good? Okay, cool. Going to jump into hypothesis testing, distribution of sample means, things along those lines. Again, setting the framework for strong understanding of what's going on when we're actually running our inferential tests. So up to this point, so the examples that we've been giving have pretty much been focused on identifying location and probability of individual values within a population of scores, right? So I'm saying, here's the distribution of SAT scores, what's the probability of getting a score of this or higher? Here's the distribution of IQ scores, what's the probability of finding a score at this level or higher, right? Here's distribution of height, what's the likelihood of finding someone who's 4'11" or shorter, right? So again, looking at identifying the location probability of individual scores within a distribution. But when we're doing our applied research, we're rarely interested in what Alicia is doing. Nothing against Alicia, I just really don't care about Alicia. Because what she's doing is Alicia's own business, right? But what I might be interested in is if Alicia's part of some population of interest, I might be interested on average where sort of Alicia's a graduate student, I might be interested in sort of graduate students' level of extroversion or something like that, right? And so what I might oftentimes be doing when we're looking with research, I'm not interested in individual score, but I might be interested in making inferences about means taken from a sample of scores, okay? And so now all of a sudden, same type of principles, we just kind of expand this out a little bit. So just as we have gone through and said, okay, how representative is a score or a specific value given a population of scores, use the same type of stuff to go through and determine the representativeness and probability of selecting a specific mean, having certain characteristics from the all possible distribution of all possible sample means. Okay, so it's the same type of principle. We're just going from the individual as the unit of analysis into the mean value as the unit of analysis. Okay, so what we're working with here, if we're talking about mean values, but this goes into other statistics that we can use, looking at the distribution of sample means. Okay, distribution of sample means is referring to the means obtained from all possible random samples of a given size that we could possibly draw from a population. before, the values in our distribution were individual scores, right? This is the individual heights or the individual IQ scores or things along these lines. With the distribution of sample means, the individual units are going to be the value of a sample of a certain size, okay? If we're thinking about how to do this in practice, it would be very hard because we can't not functionally count this. I mean, we could actually literally, if we knew how many people were in the population, we could literally calculate how many possible samples you could pull from sort of that population. Functionally, that's not available to us though, because we don't know how many people are exactly in the population. We can never go through and run all possible samples. And so this is out of our reach to do from a practical sense. But what we can do is we can take mathematics. You like that, right? Nice. I don't think that was a genuine laugh, but I took it as one.
I like it.
Well, what we can do is we can go through and mathematically, because we know that the distribution of sample means has certain types of properties, okay? So let's say, very, very basic example, we've got 4 scores here. We've got 2, 4, 6, 8, right? We go through sample of mean of these, so this is my population, just 4 scores in this population. Mean of this sample is 5. So how would you describe the shape of this distribution?
Very straight, like.
Very square, it's straight. It's a uniform distribution, it's a square distribution, right? There's no, it's certainly not normal. It's just 4 scores. Mean is 5. 5 is an actual real value that shows up in this population, but sort of this is what we're working with, right? So, but if we wanted to go through with this population of 4 scores, we could go through and construct a distribution of sample means from this population of 4 scores. And if we wanted to do that, let's say we're going to go through and we want to construct a distribution of all sample sizes, of all possible samples of sample size 2, okay? So it's not much of a sample, but for the purpose of this is what we're going to do. If we've got 4 scores in the population, this is limited and it's nice because there's 16 unique samples that we can draw from with population 2, right? So my first sample, 2, 2, 2, 4, 2, 6, 2, 8, so we're going down through 16 unique possible samples that we could draw at random with replacement in this sort of distribution, okay? People see sort of how this is working out? Okay. And then what we could do for each one of these samples, 16 possible samples that could be drawn from these 4 scores, we could then calculate a sample mean based on each one of these 16 samples. So we've got 2, 3, 4, 5, 3, all the way up to, so ranging from 2 to 8, right? And what we've done here is in this example, we've calculated the distribution of sample means. This is all possible sample means that could be drawn of a sample size 2 with replacement from this population of 4 scores. Okay? People follow me up to this point? All right. And if we go through and we plot the distribution of sample means, we see that this distribution of sample means does something very specific. This distribution, Sally, how would you describe this distribution? It starts to become very normal, right? It starts to become very symmetrical. And what we know mathematically what happens with our distribution of sample means, some things start to happen. We see that this distribution of the sample means start to pile up around the population mean, okay? And what we know from a mathematical standpoint, the mean of the sample means is going to be equal to the population mean. So this starts to become helpful because I will never know what the actual population mean is, but mathematically I can derive and start to infer what that population mean is based on the distribution of sample means. My expected value of the mean is going to start to line up here. Mean of my population was 5. Tomorrow, what's the mean of my distribution of sample means here? It's about 5, right? We see everything start to pop up. Distribution of sample means is going to generally form a normal distribution under certain types of circumstances, and we'll talk about it in a moment. And then what I can do is I can start to use this distribution of sample means to answer questions about the likelihood or the probability of selecting a random sample having certain types of characteristics, okay? So what we've done, all that stuff that we did in the last unit, talking about distributions and things along those lines, focusing on the normal distribution, well, if we're talking about means, all of a sudden we can start to use those exact same properties when we're talking about the likelihood of drawing some random sample having some specific characteristics from all possible samples of a given size. Okay. Questions on sort of this kind of really simplistic demonstration on how this stuff kind of fits together? All right. So if this is my distribution of all possible means with replication of sample size 2 that can be drawn from this distribution here, CJ, what's the probability of randomly selecting a sample having a mean of 7 or higher?
3 out of whatever the population is.
So 16.
Yeah.
So what is it?
3 divided by 16.
Yeah. What's 3 divided by 16? If we want to get up to that.
About 19%.
About 19%, right? So we can say, so would you say that that's a likely outcome?
No.
Not terribly. It's not going to be super rare, but it's not super sort of frequent, right? So basically, we're talking about these three blocks right here, right? Well, what we can do is, sort of based on the mathematical properties of the distribution of sample means, we can again start to say, all right, what's the likelihood of randomly selecting a sample of 100 undergraduates, sample size of undergraduates, 100 with a height of 5'2", average height of 5'2", right? We can start to go through and assign probability values and start to make inferences on sort of the likelihood of certain types of characteristics, okay? So as we get into using this in our statistical procedures, so we're going through, and I'm not going to make anybody sort of prove anything like that. That's for people who are actually statistics majors and econ folks and things like that to go through and prove sort of why this all works. We'll take it on face value that people haven't been misleading us for centuries. But what we find with the central limit theorem kind of encapsulates this. We find that a population with a mean of mu and standard deviation of sigma, the distribution of sample means for samples of all size n, going to have a mean of equal to the population mean and a standard deviation of the population standard deviation over the square root of the sample size, and it's going to approach a normal distribution as our sample sizes start to approach infinity. So if we're thinking about central limit theorem and what that means in terms of characteristics of the distribution of sample means, okay? The distribution of sample means is going to start to approach a normal curve if one of two things are true. One, the population from which samples are drawn is normal, okay? So someone give me an example of something in the population that has some normal distribution. IQ, okay, fine, right? So if I go through and I have, let's say I'm drawing sample size of 5. Nick, how quickly will my distribution of sample means approach normality if I'm having sample size 5 and I'm measuring IQ? Pretty quick, right? Because the underlying distribution is normal, and so even if I have small samples, I'm still going to get a normal distribution. The distribution of sample means for sample size 5, if I'm measuring IQ, is still going to hit normality pretty quick, right? But sometimes we measure things and we're interested in stuff that's not normally distributed, right? Sometimes we're interested in things like number of suicide attempts in my lifetime. I'm glad that's not normally distributed. That would be bad news if it was, right? But that doesn't mean we can't go through and use our means-based test for that, because as long as our sample sizes are about 30-ish or more, and there's nothing special or bright line about 30, it's just if you've got reasonably sized samples, still, even if we're looking at something that has a very, very skewed distribution, something like substitutes or something like that, as long as we have reasonable samples, my observed data might be fairly skewed, but the distribution of sample means for that data is still very quickly going to approach normality as long as we've got reasonably sized samples. All right, so this is sort of the shape of our distribution. If we're thinking about central tendency, the mean of the sampling distribution, or the mean of distribution of sample means, is going to equal the actual population mean. So here, if we take a random sample of adult height, so this is of whatever population we're looking at. This represents all possible random samples of size equal 100, and we've gone through and plotted out mean heights. We find the expected value of the mean. This is the mean of the sampling distribution of means. It's going to be equal to the population, right? And so this is how we can go through and start to infer things about very, very specifically about a population parameter, even though these are things that we'll never be able to observe directly. Mathematically, we know that the mean of the distribution of sample means is going to be equal to that actual population mean. Okay. People sort of follow me up to this point? All right. Last thing we can start talking about in terms of the distribution of sample means, we can talk about variability of the distribution of sample means. This is the precise estimate, at least if we're talking about standard error, the mean, or your standard error. Standard error for most of the applications that we're working with this semester, or many of them, is going to be, your standard error is going to be the standard deviation of your distribution of sample means. Okay? So this is all possible random samples of size equal 100 that could be drawn from this population. We know what the shape looks like. We know that the mean of the distribution of sample means is going to be equal to the population mean. And what we know is the variability, or the standard deviation of this distribution, is going to be equal to the population standard deviation divided by the square root of the sample size. Okay? And if we're thinking about the standard error means, so encouraging you to think about this from a practical standpoint. What does this actually mean? There's a number of different ways we can think about this. We can think about this, obviously, as the standard deviation of the distribution of sample means. We can think about, from a practical standpoint, your standard error being sort of giving you an idea of how much variability you would expect, or how much you would expect replications of this mean, how much you would expect it to jump around, either from one sample to the next, right? So if I collect random sample of height from a sample of 100, and then I do this again, and a new random sample of height with another sample of 100, how much on average should I expect that mean to jump around, right? Do we want that mean to jump around a whole lot? Nope, we don't. We want it to be pretty precise, right? And so if we go through, and this is just sort of thrown in some kind of guesstimate numbers, if we say the population standard deviation is 6 inches, that's probably too high. Let's say it is. The standard error, the mean here with a sample size of 100 is 0.6 inches. That's suggesting that on average, across replications, I'm expecting my average height with sample size of 100 to jump around about about a half an inch from sample to sample. That's pretty precise, right? So we can think about standard errors giving us sort of what to expect in terms of how likely this estimate is to jump around. We can also talk about this as how well any individual sample represents the actual population mean. Okay? We know that any sample that I get is not going to exactly equal to the population parameter, right? But my standard error tells me how close I'm likely to be. So on average, with sample size 100, given so what we know about the distribution of height in the population, if I've got a sample size of 100, as long as I've got a reasonably representative sample, if there's not something screwy about my methods of collecting, I know that that's probably going to be pretty close to the actual population parameter on average in general, right? Now, Nick, is it possible to get a sample that's way out here? It's possible, right? I can do that, but on average, all other things being held equal, I'm expecting that probably I'm going to be within a half inch of the population, sort of based on what's going on, right? So here we're talking about replicability. Here we're talking about validity and these two things are, it's like, did I write the same thing? Okay, expected difference between the sample mean and the population mean. So both of these talking about sort of error and the validity of my sample, right? So if I'm trying to measure graduate student income, and my standard error is 2,500. Do I have a very good estimate? No, that's not good. That's a lot of jumping around, right? If I have a standard error of 300, that's much better, right? That's sort of starting to get much, much closer. And again, what's driving this standard error estimate is going to be your sample size. The larger the samples we have, it's going to shrink that standard error down. We often can't do much about the standard deviation, right? But that sample size is going to help us get much, much more precise estimates, so we have greater confidence that whatever value we get for our mean or whatever it is that we're measuring is going to be hopefully pretty close to the actual parameter that we're trying to capture. Okay, so we're thinking about distribution of sample means in terms of shape, central tendency, and variability. Questions on this? Okay, if you guys want to get liquored up and have a good time, up here is a link. So this is just like a really, really important concept. So I have a screencast video sort of going through an SPSS and generating sort of random data. You can start to see, even if you go through and sort of manufacture data that are normal or terribly skewed, how quickly all of this stuff actually works out in practice. Like, it's not just, oh, in theory this should happen. It's shocking how quickly this stuff starts to conform to your estimates of standard error and things along those lines. You don't need to do this, but if you're interested and you're sort of struggling with or sort of wanting to get a good handle on exactly what's going on, so it's a screencast of just me and SPSS going through, here's a data set, let's just draw random samples for it and how quickly that distribution starts to become normal, even if we have crazy skewed data and things along these lines. Okay, so things that are influencing our standard error, our population standard deviation. Okay, standard error decreases our population standard deviation. This is that as our sample size gets larger and larger, the closer and closer our sample is going to be likely to be to the population mean. As we get more and more people in our sample, assuming that we've done a good job, our samples are going to get more and more representative. We're just going to get more and more precise estimates. I had talked about from central limit theorem, this idea that your samples are going to start to become normal, either if the underlying distribution of whatever you're measuring is normal, if your sample size is reasonably sized, about sample size 30 or so. This is kind of sort of around the same type of thing. If we take a look and plot out the standard error as your sample size divided by the square of your sample size, if this is your sample size, you'll see as we start to get sort of very, very low, tiny, sort of less than 20 samples, standard error is pretty big, but as it increases, it starts to decrease rapidly. When you hear people say, oh, a sample size of 30, that's a large sample. 30 is not a large sample. That's a small sample. But from a mathematical standpoint, when we hit about 30-ish, is we start to see incremental increases or reductions in your standard error start to asymptotically kind of flatten out. Now, if we were to carry this out to 500, like, it would still be going down. Bigger samples are always going to be better, right? But this is kind of the mathematical basis. When you hear someone say, oh, a sample size of 30 is sort of big, that's kind of what's going on with that, is that sort of standard error just starts to flatten out a little bit. Okay. So again, just a graphic here showing distribution of sample means. If we have something, distribution of sample means for IQ scores, right? You've been using that. If I'm going through and I have sample size, say 10, right? My distribution of sample means for sample size 10, 30, 50, 100, right? We see, Chris, what's the expected value of the mean for each one of these distribution of sample means?
100.
It's still 100, right? It's equal to the population mean. But what you can see is the distribution of sample means, if we're measuring IQ, as our sample size starts to increase, it starts to get less variable, right? Our standard error starts to become tighter and tighter. Here, we're all over the place, right? But as our samples start to get larger and larger, the amount that we're expecting our mean estimate to jump around starts to get much smaller. Now, this isn't to say that we can't get a weird estimate, right? Sometimes we're just gonna grab a random score, even if we've got best practice methods, right? We can still grab something way out here. That's possible, right? But this is where it starts to become crucial that you have a strong basis in sort of your area of study. And hopefully what you're gonna be able to do is recognize that if I'm studying IQ and I get a mean score in my sample of 100 of like 120, yikes, right? It's not impossible, I could do it, but it is an infinitely small chance that that's actually gonna happen. What I'm gonna do probably first is go through and make sure my methods are good, that I'm scoring things right, that I haven't sort of stumbled on a nest of super geniuses, and sort of not report that as like, oh yeah, this is just something that happens, right? Again, what you wanna do is sort of know enough about what you're studying so that you can sort of get a gauge of whether or not you've just happened to stumble on something that's way high or way low here. All right, so we've got three different distributions here. We've got the distribution of population scores. This is all scores in the population, right? Distribution of our population has its own shape, mean, and variability. And we've got the distribution of a sample of scores. These are the scores that I've collected from my study, right? My sample is going to have its own mean, shape, mean, and variability. And then I'm going to have a distribution of sample means. This is the sample, all possible sample means of a specific size that could be collected from the population. It's going to have its own mean, shape, and measure of variability. So thinking about, and this does become important when we think about what we're trying to do with our statistical methods, this is what we're interested in, right? This is always what we're interested in, but we can't know this. Or we rarely know this stuff. So what we do is we get a sample, right? Alicia, does this look like this? No. No, right? Is this equal to this? Close, right? But sort of not too bad, right? But this is nice and beautiful. That's pretty busted looking, right? But then if we go through and we use, so this is what we want to get at. This is what we're able to capture. This, the distribution of sample means for a means-based test, this is what we're using to go through and start to infer how likely is it for me, assuming a mean of 100 and a standard deviation of 15 in the population, how likely is it that I would grab a population or a sample with these characteristics? This is what I'm using to go through and assign that probability. All right. So again, primary function of this whole process is to try and identify the likelihood of obtaining a sample with certain characteristics based on our assumed model, right? Up to this point, we're assuming that our distribution of sample means is normal with mean equal to population means, right? So we can ask the probability of randomly selecting a sample with mean M, assuming a normal distribution, and this is where our z-scores are going to come in. So we're taking this out of the realm of identifying the probability of a score, an individual score in a distribution, and trying to assign probability to obtaining a sample of certain characteristics based on sort of the underlying assumptions of our model. So our z-score here, we're going to take the mean of our sample, we're going to subtract the population mean, or sort of whatever we assume the population mean to be, and divide it by the standard variable mean. I'm sort of cooking through. Is anybody like lost or confused or need to pump the brakes on any of this stuff? I don't want to go on and on about it too much if it's mostly review, but it's just kind of the foundational sort of components of this. Is people okay with this? All right. So let's say that we wanted to calculate SAT, say the SAT scores, normal distribution, mean of 500, standard deviation of 100. Want to know what the probability of selecting a random sample of 10 students with mean SAT less than 440. So again, this ends up being not too terribly difficult. You know, mean is 500, standard deviation 100, sample mean is 440, sample size of 10. Okay. What do we need to do first in order to solve this? Tyler, what do we want to do first? What's that? Yep, want to calculate the z-score. What do we need to first to get the z-score that we don't have already? Someone help her out? What do we need?
Oh, the standard deviation of the distribution, right?
Okay, yeah, so we got,
Yeah.
so we got that.
We need to, don't we need to convert that to like,
Yeah, with the M.
What's that? Yeah.
yeah.
Yeah, what do we call that thing? Standard error.
That's
Right, I
right.
told you standard error was always the right answer. Beat me in. All right, so standard, so this, that's just standard error to me, right? And so what we're gonna do is we're gonna take, and we know what the population standard deviation is, right? So we can use that. And so we say 100 over the square root of n is 10. And so what's my standard error for this? What do you got, Alicia? Tell me what you got. What is it? 31.625. Is that what we got? Okay.
That's a square root.
Yeah, yeah. So this is our standard error? Okay, perfect. All right. What do we do with this? What do we do with this now, Nick?
Drop it on the bottom.
Drop it on the bottom. That's right.
Drop it like it's not.
We do drop it like it's hot, right? All right. So we got, or people do, I don't know. All right. So we got, all right. We got 440 is our observed mean, right? Minus sort of what we know the population mean is divided by 31.625. What does this give us in terms of our z-score? What do you get tomorrow?
-1.897.
Is that what everybody else got? Okay. So, what is the probability then of randomly getting a score or a sample size, sample of 10 individuals with a score of 440 or less? How do we go through and to get that probability? Z-table. Does anybody have their Z-table up right now? Let's pull that up.
Is it like 16%? Rough guess.
You can certainly do so. We would get a little more precise than that. What is our probability here? What's that?
Which column would you
Okay, so we've got
less than?
this distribution here. Where's, if this is 500, where's our score on this, right? This is 1.897, so 1.9 now should on the table, right? So this is what we're looking for. So what's our probability?
Just below 3%.
Just below, can you give me what the actual?
0.0294.
0294. Okay, is that right? Is that everybody pulling that up? Okay, cool. So this is not likely, right? To get a sample of 10 individuals with a score of 440 or less, if these are randomly selected individuals, this is very unlikely, right? So we can say, boy, if the actual population mean of SAT scores is 500, this is a very unlikely sample to get as long as we've randomly selected and also if all the methods are good and things like that, right? Well, what if we go through and let's jack up the, keep everything else the same, but we just jack up the sample size, right? So what's the likelihood of selecting a random sample of 75 students with a mean SAT score of less than 440? CJ, what do we have to do to solve this one?
Can you repeat that, sir?
What's up?
Can you repeat that?
Yeah, so what do we need to do if we want to solve this second piece of things? Based on what we've already calculated. What's changed? Our sample size. And sample size is going to impact what?
Standard error.
Standard error, right? So we're going to go through and recalculate this for the second one here. So we've still got population, standard deviation is 100, except this time we're going to take the square root of 75, okay? Someone give me my standard error here. 11.547, okay? And we've got Z equals 440 minus 500 over 11.547. Okay. What's my Z score now?
Negative 5.196.
Negative 5.196. Okay. What's the probability of getting? What's a probability in the lower tail for a Z score of 1.96? It's probably not even on the table. Right? Okay. What happens? So if we look at this and I'll show you. If one of these. The interwebs is a fantastic place. So this GraphPad website, I've got this bookmarked because it's nice to be able to just go through and drop things in. So what's my Z score here?
Negative 5.196.
5.1.
Number one.
Oh, okay. Okay, it's not even, it just says just less than 0.0001, right? So it's sort of an infinitely small possibility. So what happened with this? What caused? So we've got the same score. We've gone from a sample of 10 to a sample of 75. What we were doing wasn't likely when we had a sample of 10. So this average score of 440 wasn't likely when we had 10 people in the sample. But as soon as we calculated a sample of 75, now all of a sudden that's functionally close to impossible to actually get that if we're giving it a true case. Right? It's basically like winning the lottery, right? What happened?
Because you're getting too far from the mean, because your sample size is getting larger, and you're trying to look at a score that's getting too far from the mean.
Okay. Well, the score is still the same distance from the mean, right? In both cases, we're still 60 points.
Sorry.
We're still 60 points under the mean.
The likelihood of that, of getting someone with that score is less.
Is getting less, yeah, but why? What's happening? What's happening here? Why is it getting less?
Captured more of the sample.
Okay, so it's getting more of the sample, right? So for me to go through and snag a group of 10 people whose average SAT score, if they're randomly selected, to get someone with sort of a score that's randomly 60 points below the mean is really unlikely, right? Well, my sample size is just 10, right? I've just gone through and grabbed 10 people, and so maybe what happens, I just have maybe some people and then someone just like an extreme low score or something along those lines. My distribution of, so here's 550, and here's 440, right? But with n equal 10, my distribution of sample means is something like that. It's down here on the tail. It's not likely, but I don't know, if you told me I had a 2% chance or 3% chance of winning the lottery, I'd certainly be buying tickets, right? But if we take the same situation, 550, 440, this time I have n equals 75. My distribution of sample means is the variability here is shrunk down considerably. My standard error with a sample of 10 is, what, 30 something? My standard error with a sample of 75 is 11 and a half. What's going on is it's the same difference, right? The likelihood of me grabbing a score of 10 people with this characteristic or lower, I've got more variability in that distribution of sample means. As I jack that up, what ends up happening is my variability around that gets shorter and shorter. It's the same difference, but now it's just hanging out way, way outside of me. It makes it sort of functionally sort of nearly impossible to randomly get a score, 75 people with an SAT score that low on the end. Kind of seeing how sort of this is working and from a mathematical conceptual standpoint, sort of how sample size is driving our ability to, or sort of likelihood of getting sort of an increase in extreme values. Okay. All right. So if we're trying to interpret sort of some of the things that is going on in our data, a couple different explanations, some things that we can sort of draw around some hypothesis tests. This pattern is caused by some systematic factor, right? What we've done is we've actually captured some actual population effect, right? There's some association, difference, something that's going on that we've actually caught. That's what's going on when we're seeing patterns, right? Also, possibility that our pattern is just chance fluctuations. We just got random noise, things along those lines. This is generally, when we're going through and talking about statistical inference, these are generally the two things we talk about, right? Have we found a true effect, or have we just found something that's just random noise or things like that? Okay? At this level, the doctoral level, I want you all to be thinking about another possibility. The pattern is a result of systematic bias or violations of the underlying statistical model. Remember that everything that we're doing is based on a mathematical, sort of based on the assumption of a mathematically pure sort of system model things going on, right? We can also start to find things that are because our samples aren't representative, or our methods are terrible, or other types of systematic biases that are sort of going on because I went through and I decided what my hypotheses were after I ran all my statistical tests, and then I generated some hypotheses tests after I looked at all the p-values, right? So these are some things that go through, and again, that's bad news, yikes. We've got spooky violations, we've got distributions that we don't understand what the characteristics are because they're unknowable, and we're spooked and scared about that, right? But we always want to think about, like, what's the possibility that what I've done actually doesn't reflect sort of a true effect? Is it something that's gone on, or I've gone through, or Chris has done, that you put your thumb on the scale, knowing they're not, and that's why we're seeing effects, right? So, our approach is to use, so one of the things we try and do, to try and sort some of this stuff out, is use our significance tests to try and facilitate our statistical inference, to try and tease out what might be due to an actual effect versus what might actually be due to just general static, right? What we want to do is try and identify and differentiate between sort of true effects, actual real effects, and sort of just random fluctuations. But always remember that we can't correct, there's no statistical test that adjusts for really terrible methods, right? I can't go through and post hoc control for the fact that you've got a terribly biased sample, right? And our statistical test won't tell us if you have a terribly biased sample. This is something that you have to go through, think about based on the knowledge that you developed in your area to try and say, does what I've done make sense? Do these results make sense? How does this all fit within the context of underlying assumptions, procedures, critical evaluation of the methods? All right. Overview of our tests here. So what we want with our hypotheses tests is we want to, again, always draw an inference about the population. If you tell me, when I ask you to give me a statement of the null hypothesis and an alternative hypothesis, you say the null hypothesis is the mean of the sample is something, you're going to get that wrong, right? I don't need to run a hypothesis about what the mean of the sample is. I can see what the mean of the sample is. My hypothesis is about a population. That's what I want to do. I want to learn something or infer something about a population value, okay? Now, I don't have access to the population, so what I can do is I can draw a sample and then try and start to infer something about this, right? So if we assume that a population has a mean of some value, what we want to know is what the probability of drawing a sample from that population with mean characteristics of M or more extreme than the one that's observed in our data, okay? So here, we've got a rat population. Rats are nice because they're bred to be genetically identical to one another. We know what the characteristics are, and we know that the population of lab rats has a mass of 400 grams. Okay? So what we're going to do then is we're going to go through and we're going to draw a sample of these rats with a population we know has 400 grams, and we're going to give it some treatment. Right? We're going to give it steroids or restrict its diet or give it a supplement or do something like that. And as soon as I do that, now I have a sample of rats that aren't part of my population, right? I've got a sample of rats that represent some hypothetical population. So if all rats were to receive whatever treatment I would have, then this is the population that we would expect, right? Now, I don't know what the mean mass of the medicated rats are. But what I do know is I've got this sample of rats that I've medicated. And what I want to do is I want to go through and say, based on the sample of rats that I've got, what are the regional values for the population of this potentially new population, right? This is a hypothetical. There's only, say, sort of 15 rats that have ever received this treatment. But they reflect a hypothetical population. If we were to give this to everybody, what would be the population of this? Now, if we want to see if this has made a difference in our, if this treatment has made a difference, what we might do is we might compare sort of the sample statistics we've got this against the known population of rat mass here, and try and say what's the likelihood, assuming that the population of medicated rats, this unknown level, assuming that it's equal to the population mean of general rats, what's the likelihood of obtaining a sample of this size with these characteristics? So let's say, so this is 400, let's say my treated sample is 410, right? What's the likelihood of me collecting a randomly selected sample of rats, assuming a mean mass of 400, having a sample, an average mass of 410 grams, okay? And then what we can do is assign a probability of the likelihood of having that sort of based on our characteristics here, right? If its probability is determined low, right? It would be very uncommon to randomly draw. If this rat population has a mean that's equal to the known population here, it would be unlikely to randomly select a group of rats with mass 410 if the population value was 400. Then what we're likely going to do is we're going to conclude that the population from which the sample was drawn has some mean that's different than what's assumed under the null hypothesis, right? If, for example, this wasn't sort of the estimate we did here, and let's even say, let's go down to the 10. Now, let's use this, okay? Let's say that I have some group of students, right? And I say, maybe this is a group of students from inner city schools, impoverished schools, right? And so the hypothesis is, does school poverty have an impact on SAT performance, right? And maybe the hypothesis that I'm testing against is that, well, I've got a group of students from low impoverished communities, right? And let's assume under the null hypothesis that these students have the same SAT scores as the general population of high school students. What's the likelihood, if that's true, if all the population of students going to these impoverished schools really do have a mean SAT score of 500, what's the likelihood of me obtaining a sample of 75 students with an average score of 440, right? And if I find that it's infinitely unlikely for me to have found this sample, if the actual population parameter is what we think it is, then we would likely to include under sort of our null hypothesis statistics testing. We would assume that it's likely that this sample was drawn from a population that has a mean level that's somewhat different than what we know, right? It's functionally impossible. If the average SAT score among students from impoverished schools is 500, this sample is functionally impossible. And so then what we go through and infer from that is that likely that students from impoverished schools probably have a mean of something very close to 440 or around there, depending on the precision of our estimate, right? So this is the logic of our hypothesis testing. What we're wanting to do is we're saying, assuming that the null hypothesis is true, assuming that the null, that the mean mass of medicated rats is 400, how likely would it be for us to obtain this sample? Questions about sort of the logic of what we're working through in this? Okay. Okay, so let's go through an example here. We say that we've got, and we believe antioxidant supplements might reduce, possibly reverse age-related cognitive decline. So thinking about supplements as a way to improve cognitive functioning in older adults. We have a sample of 25 adults aged 65 or older, take antioxidant supplements for 6 months, and then we give them a neurological test to determine overall level of cognitive functioning. This assessment we're giving them in the normal population of adults 65 and older. We know that the average score on this assessment is 80 with a standard deviation of 20. And our previous psychometric research suggested if we get scores deviating by 10 or more points from this, that starts to have practical implications of stuff. You're kind of following along in terms of the example here?
Would that be a really big standard deviation?
What's that?
Would that be a really large standard deviation?
Yeah, and again, this is what I sort of tried to kind of make up and things like that for the purposes of this, but you're right. If we're thinking about what we can find and thinking about like clinically reliable change and clinically significant change, like for example, for the PTSD checklist, the PCL, in general, sort of based on stuff that they've done with veterans, a change in more than 10 points is considered statistically significant, right? Now, the standard deviation and variability of scores on this is going to exceed 10, it's going to jump around. But if I go through and I see within a person change of 10 or more points in a PCL, that is typically what is known as, sort of, this is a clinically significant change. It's something that's deviating by sort of more than what we would expect just from random fluctuations. So I kind of made this up, but you're on the right track in sort of questioning kind of how this would work. But for the purposes of this example, just kind of what's going on. But nice, you're on the right track. Okay. Other questions about the setup here? All right. So for these questions or these problems, what I want you to do, we're going to state the hypothesis, right? What we're doing here, we're predicting the characteristics of our to-be-collected sample, right? We don't state hypotheses after we've gone through and done the study. Always wanting to do this on the front end. Then we're going to set the probability criteria for what we're going to determine as statistically significant or reliable effect. We're going to collect the sample data, compute relevant statistics, and then we're going to draw conclusions based on the data that we've collected. So, statement of the hypotheses. Really working with a couple of different things here. the null hypotheses, almost always, and this is not the way it has to be, but it's the way that we do things. We're going to talk about ways we might do things better, but in general, what we end up, the null hypothesis ends up being a point null where we say there's zero association between the IV, independent, the dependent variable, and large population. The manipulation has no effect on outcome. The average score in the population will be equal to some known value or something along these lines, right? The difference is going to be between group A and group B is going to be equal to 0, okay? This is our null hypothesis. This is our point null that we're generally testing in traditional statistical tests. Our alternative hypotheses, we're going to say some non-zero association exists. The correlation is not 0, right? Or the difference between group A and group B is not 0. Something along those lines. We're saying that whatever, if we're doing manipulation, has some measurable outcome on sort of the thing that we're doing, right? So we've got the null, we've got the alternative. With our traditional null hypothesis testing, this null hypothesis here is the only hypothesis of concern. It's the only thing that's actually being tested, right? Our tests are focusing on whether or not this point estimate that we've got is exactly 0, right? This alternative hypothesis is kind of a complement to our null, and we're not specifically testing the alternative. The alternative actually a number of around whole sort of variety of different hypotheses. The null hypothesis tends to be, in the way we conduct science, a point null that some parameter is equal to 0 exactly. Questions about this? Okay, so the null is our focus. So when we're talking about a statistical model, the statistical model we're talking about is our null model, okay? If we're talking about our statistical models, we're talking about a set of assumptions about how the observations we've found or observed in our data were generated, okay? So if I'm looking at sort of some population with a value of 80, standard deviation of 20, right? What I'm looking at here is that I'm saying that so the data that I'm getting is generated by random draws from a population with a mean of 80 and a standard deviation of 20, assuming a normal distribution of the distribution of sample means. Okay? So what we're doing when we're typically working with our null hypothesis testing is we're saying, oh, so the mean value is 0, right? The correlation is equal to 0. The difference between group A and group B is equal to 0. That's kind of what we're focused on in terms of our point estimate. But if we're actually getting into what's going on, we've got a whole lot of other things that are going on. We've got what we call these auxiliary hypotheses or auxiliary theories that are kind of accompanying along, right? And these are implicit assumptions. The other stuff that's going along are things like we're assuming that the sample is representative, that it's randomly selected, that the distribution of sample means is normal, that the model is correctly specified. Anybody have an idea what we mean when the model is correctly specified? We're saying that anything that needs to be in and measured is being measured. Anything that doesn't need to be measured isn't being measured, right? So if I'm looking at, so you do like in-group, out-group types of stuff, right? So if I'm measuring in-group cohesion, that everything that's relevant to understanding in-group cohesion is included in my study. Is that how studies are run? No, right? Our statistical models are a gross oversimplification of stuff, but what can happen is if we start saying, oh, I have a relation between X and Y, that could be, if my model's not correctly specified, if I don't have things in my model that need to be in there, that can be just a spurious correlation. It's not because of whatever it is that I measured, it's because of some other thing that wasn't in the model, right? And so that's going to start to impact my inference. Maybe the relation between X and Y in the population is actually 0, as long as we've got this other thing accounted for, but because I left it out, now all of a sudden I'm getting biased results of that population estimate, right? Measures are valid. Measurements are collected without error. How often do we measure things without error? Never, right? Hypotheses were generated prior to the evaluation of the data. This starts to become important, right? So the probability of me finding things that are statistically significant after I've checked to see if they're statistically significant is 100%, right? And so all of these things get sort of tied into the assumptions of our model, but we don't think about this stuff, right? We just go through like, oh, our estimate is that the difference between these two estimates is gonna be 0, right? And as we start to ignore this, this can start to lead us into, or sort of cause us to make misleading inferences based on our studies and the studies of other people, okay? So again, the validity of our estimates are 100% predicated on sort of our underlying model and all of the associated inferences that are sort of tied up with this, okay? So again, this is just reiterating that we can't divorce statistics from the methodology when we're trying to draw strong inferences about what we know about different things. And to get the concept of what the statistical model we're testing is, and it's not just one thing, it's sort of a lot of different stuff going in. Okay. So, for a supplement example, so this is giving you language that you might use in a future problem set, right? So your null hypotheses, mean of the memory score in the supplement group is equal to 80. Average cognitive functioning score in population of older adults using learnable supplements is equal to 80, right? We're saying that these adults, population of older adults using supplements, their average memory score is equal to the general population. It's no different. It's the same as sort of all adults. Our alternative hypotheses here, being that our supplement mean is not equal to 80. So this is a non-directional hypothesis. We're just saying it, I don't know, it might be above, it might be below. In general, we probably have ideas based on our thing that says it's probably above, but we're just saying for our alternative that it's not equal to 80. If we're saying this out loud, cognitive functioning, population of older adults taking herbal supplements, not equal to 80, okay? Please attend to this as you're going through, and I'm asking you to go through and give me statements of the null and alternate hypotheses. I want you to tell me that you understand what the population is that we're talking about and what we're measuring, okay? This isn't just me being tedious to force you guys to jump through hoops and things. My goal here is to sort of get you ingrained in thinking about anytime we're running statistical analyses, at the end of the day, there's a population in mind that we're trying to infer something from. And we're not just running numbers to run numbers, there's something that we're actually trying to measure with this, trying to get that all wrapped up. When you're going to see sort of average, or sort of the mean is not equal to 0 or something like that, I want you to give me a little bit more to sort of set up the problem. Okay. All right, so we've gone through and we've set the hypotheses. Want to set the decision criteria, probability of obtaining the sample, assuming the null hypothesis is true. This is sort of the criteria that we're going to go through and draw our statistical inferences. If we find that our sample means found much different from what we expect the population to mean to be, we interpret these data as incompatible with either the null hypothesis or the underlying assumptions of the model. Our null hypothesis testing doesn't tell us which one it is. So I get a very low p-value. I get a p-value of 0.005. That tells me that the data I've drawn are incompatible with the null hypothesis or something about the underlying assumptions, right? I don't know which one of those two are. I mean, we tend to focus on this, but it could very easily be I've gotten a low p-value because my methods are invalid, my sample selection is off, because my data don't conform to the underlying assumptions in terms of the shape of the data and things along these lines. I don't know based on that which one is going on. All I know is the data that I've got and I'm observing are not compatible with the underlying model that I've laid out. Okay, so we have to be careful with that. But on the other hand, if we have sample means that are similar to the hypothesized mean, we generally say that the data are compatible with the null hypotheses. Our statistical procedures are telling us whether our data are unusual, right? But it doesn't, so this is the other thing, it doesn't tell us that the model or any aspect of that model is correct. So this is what happens sometimes. So I find that my p-value is very large, right? And so I say, well, it looks like the null is true. No, that doesn't tell you that the null is true. It just says that the null, that these data are consistent with what would be expected under the null hypothesis, But once again, we don't know if that's because there's no effect in the population, that the null is true, because there's something wrong with our assumptions. So we wanted to be careful about not over-interpreting either very, very small p-values or very, very large p-values. And so this threshold that we set for determining whether or not something is likely or unlikely is set by our alpha level. We set this at the front end, use this to identify critical regions. We can say we set it, we really don't set it, because I can't just make my alpha whatever I want it to be like. There's conventions. If I set my alpha at 0.2, I'm probably gonna have problems getting that published, right? There are arguments for, in certain cases, let's say I want to, this thing that I'm doing is very, very important that I not miss something if it's there. And so maybe I set my alpha to 0.1, because so whatever I'm doing, whether it's for public policy or public health or something like that, it's important that if there's a signal there, I want to make sure that I can get it. Then maybe I can make an argument for setting my alpha level lower. Or if I'm doing something, I've got say a medical procedure that I'm studying, and the side effects are bad, and they include possible death. Maybe I crank up my alpha level, because I don't want to make a type 1 error and say, oh yeah, this is a good thing to start doing in mass procedures if it's not actually working, it's putting people at risk, right? But in general, for the types of stuff that we do, our alpha levels are right around that 0.5 level. Okay. So again, for our supplement example, this is a distribution of sample means. So assuming the null hypothesis is true, all possible, capturing all possible samples that could be drawn from the population. Our alpha level is 0.05. For our test here, we're going to say here's negative 1.96, positive 1.96. If we find test statistics that fall within the body of the distribution, we're going to say, okay, those are data that are not necessarily incompatible with the null hypothesis and underlying assumptions. If we find values that fall out here in the critical regions, we're going to say, yep, these data appear to be unlikely, assuming the null hypothesis is true. Next, we'll go through and calculate our statistics, right? In our very, very most basic example here, what we're going to be doing within these examples is we're going to use a one sample test where we're testing against criteria with a known mean and standard deviation. So let's say IQ scores or something like that, where we know what the population mean is, we know what the standard deviation is, and we're testing against whether or not the population that we're interested in is equal to some reference population here. So we go through sample statistics calculated based on the data compared to these known population parameters, calculating confidence interval, as we outlined before. Then we can also calculate our test statistic. Here we've got a z-score, and what we're doing is this z-score is going to tell us the position of our sample relative to all possible samples of this size, assuming that the null hypothesis is true. Right, so our test statistic here, always important, make sure you don't get your test statistic confused with your critical z, but again, follows the same structure. We've got our observed mean minus the population mean under the null, divided by our standard error of the mean, standard error, just like before, is population standard deviation divided by the square root of n, just doing the same z stuff that we've done previously, or done up to this point, okay? So again, wanting to focus on the ratios here, sort of knowing what's happening, and thinking about what this means in terms of practical, sort of conceptual sort of stuff. So our numerator here, this is sort of literally the difference between sort of what I've got and what I expect under the null. So how close is what I've observed from what I expect under the null, right? So this is just a measure of distance. The denominator, this is your standard error. This is telling you, based on the sample that I have and the population standard deviation that I know, how much would I expect any randomly selected mean to jump around relative to the population parameters assumed under the null hypothesis, right? So if we're thinking about critically what's going on here, I've got what I've observed over the top of what I would expect just based on random fluctuation, right? Just based on random noise, my standard error is telling me how much I would expect this to be jumping around, right? And so if what I've observed is much greater than what I would expect, just based on random variation, what's going to happen in my test statistic? What do you think, Chris?
So what you observed is much different than what the population is?
Yep.
Okay. Then your test statistic's going to be larger.
And yeah, and so what's that going to sort of, what am I more likely to do if my test statistic is larger?
You're more likely to, I'm hoping I'm not saying this wrong, reject the null?
Yep, exactly. I'm more likely to reject the null, right? So if what I've observed is much, much different than what I would expect, assuming the null hypothesis is true and sort of based on what I would expect, just based on random variation in terms of stuff, I'm much more likely to reject, right? But if what I find is the deviation that I'm observing between sort of my assumed value under the null and what I've actually observed, if that difference is about what I would expect just based on random variation in terms of replication and stuff, then what I've got is kind of what I would expect based on random variation. I'm much less, more likely to fail to reject the null hypotheses, right? And so again, just wanting you to focus on not just like saying, oh, this is how I calculate and plug things in, sort of taking a look at this, at these ratios and saying, okay, what exactly is going on? How does this help me understand sort of what we're actually calculating? All right, where are we at? All right, so if we take scenario 1, looking at the z-statistic of individuals taking antioxidant supplements, scored an average of 92 points on the neurological assessment. So we remember we've got a mean of 80, standard deviation of 20. Second example, same thing, mean of 25 individuals, average score of 84 points. Okay. So scenario 1, I've got an alpha level of 0.05, my critical values plus or minus 1.96. If I go through and I calculate my confidence interval, my point estimate here is 92. My 95% confidence interval, 84.2 to 99.8. It's going to give me a z-score of 3. Okay, that z-score of 3 falls in my critical region. It falls beyond that 1.96. My p-value associated with this z-score of 3 is 0.003. Here's your graph pad link that you can go through to get there. And what I would do in this case, under traditional hypotheses testing, I would reject the null hypothesis, right? And I would conclude that these data are very unlikely, assuming a population mean, or a mean cognitive functioning in the population of older adults using supplements. If that actually were, if they did have a mean of 80, this would be very unlikely, right? Second scenario, we have a mean cognitive functioning score of 85. Same thing, our critical cut scores here, plus or minus 1.96. But here, my samples has a mean value of 84, still above our mean, our expected mean of 80, right? But here, my confidence interval, lower bound and upper bound estimates for the population parameter that would be consistent with the data that we've collected, anything from 76.2 to 91.8, right? And so something that's sort of closer, our z-score that we would calculate here is going to be 1. Our p-value, 0.317 here. What are we going to do, Chris, here in this example?
You're not going to reject the null.
Yeah, I'm going to fail to reject the null hypotheses, right? And we're going to conclude that the data that we've observed are compatible, not incompatible with the assertion that the actual mean functioning score in older adults taking supplements is equal to 80, right? It's higher, but it's not incompatible. Wouldn't be strange to find pull a randomly selected sample with these characteristics. Okay, all right, we'll leave it at that. We'll pick up on two-tailed versus one-tailed tests on next Wednesday. Questions about any of this stuff that we've covered up to this point. Again, all of this is really kind of fast. I just don't want to get too bogged down in all of this stuff, but I also want to make sure that people are rusty with the basic sort of underlying processes and actually what's going on with these hypotheses tests, that you're on board with stuff before we start jumping into assumptions and data and some of that stuff. Okay. Questions on anything? that stuff? Okay, cool. What I'll probably do